Hello, class. Today we're going to talk about solutions to the inhomogeneous state equation. So as I mentioned last time, for the homogeneous case, solving it is simply a matter of finding the state transition matrix, phi, capital Phi, of t naught, where t naught is the initial time and x naught is the initial state at that time. Okay, so this problem is given this linear time invariant system or linear time system with this initial condition, how to solve that. So what we do first, following what we learned in differential equations, is we assume a solution. So let's assume the solution of this form. X of t is equal to the state transition matrix times x naught plus the integral from t naught to t times the state transition matrix t tau times b of t, or b of tau, u of tau, d tau, right? And so in this scenario, it's actually the case where we're considering b to be a function of time, potentially being a function of time as well. Okay. So this implies that x of t is equal to b of t tau, x tau plus, so what we can do here is we can recall from our properties that, I can write it down here, that phi of t tau can be broken up into phi of t naught and phi of t naught tau. Okay. So now if I take this, insert it into this guy above, note that, so note that this first term has no dependence on tau. So that means that we can pull it out of the integral. So we got yeah, great. Oops, like I said, we can pull this out of the integral. Okay, so then that's just our state transition matrix. T naught, T, B tau, U tau, D tau. All right, next we note that we have phi of tau, we have phi of t naught and a phi of t naught here. So we can go ahead and pull that out. So now we get x of t is equal to phi t naught times the quantity x naught plus t naught t, oops, phi t naught tau b tau u tau d tau. Oof. All right. So now if we take the derivative of this guy, take the derivative of x of t, we get x of t dot is equal to phi dot t tau x naught plus d dt times the integral of t naught to t phi t naught bt u tau d tau. So now we can note that the derivative of the integral term is, in general, let's say we have a d dt times the integral t naught to t f of t tau d tau. This is going to be equal to f of t tau evaluated at tau is equal to t plus the integral of d dt times f, or of f t tau d tau. Okay, so essentially the derivative term, well, first you do the derivative of the integral. That gives you the function evaluated at tau is equal to t. And then you get the function, the derivative inside the term due to the product rule, or the chain rule. Yeah, chain rule. So then we get that x dot is equal to a of t v t naught x naught. Okay, and so this is right here is from our properties that I presented last class, or last video. So then this will be plus what's inside the integral, t and t, b of t, u of t, plus the integral of t naught t, d dt, dt tau, and then see if I can write it under b tau u tau. Maybe I'll put a bracket here, and then d tau. So this is right here. All right. So now let's keep going. So now we have a of t, t tau, t naught, x naught, right? Due to the property, again, the properties of the state transition matrix as I presented last time. This term right here, where the two arguments are the same, this guy is going to be equal to, this guy's going to just be equal to the identity matrix. Okay. So then we just get b of t, u of t. Then we take the derivative of the integral inside the integral. So I'm going to go ahead and start that under this, plus, just erase that, little ellipses there. Okay, so this is going to be equal to, so the derivative of this term here of the state transition matrix is going to pop out it's going to pop out this a term here. So then we get a of t times the integral of t naught t, t tau, b tau, u tau, d tau. And again, let's bracket this. Great. Almost there. So now this will be equal to, we can pull out the a's. Then we get phi t naught, a naught, plus T naught, T, phi, T tau, B tau, U tau, D tau, plus B of T, U of T. All right, and what this guy is right here, we just saw this, right? So if we go back up to the top here, we just saw this. This is our assumed choice of the solution here. So now if I scroll back down here, this guy is actually just x of t, right? So now we get, at the end, we get that x dot of t is equal to a of t, x of t, plus b of t, u of t. Great. So this means that we can easily find the evolution of our system if we have the state transition matrix and the state functions, right? So if we have a and b, and we can find the phi through various means, then we can go ahead and solve. We can solve this equation right here explicitly to get our solution of the system, to get the evolution of our system over time. Okay. So name more specifically, we can solve for the solution to x dot is equal to a of t, x of t, plus b of t, u of t, using the equation x of t is equal to phi t naught x naught plus the integral t naught to t times the state transition matrix t naught times the control matrix. There should be a tau. Yeah, this should be tau here. U of tau, d tau. Awesome. So now let's look at an example. Okay, so let's consider the example. Example LTI system with dynamics given by x dot is equal to 0, omega minus omega 0, x plus 0, 1 with initial conditions equal to 1, 0. Okay. Make sure that you guys can see everything. Okay, great. So the state transition matrix for this guy is equal to phi t naught is equal to the cosine omega t minus t naught sine omega t minus t naught minus sine omega t minus t naught. And lastly, cosine of omega t minus t naught. Close that one. Great. Okay, so before we move on, let's look at this. Let's look at this state transition matrix and make sure that it satisfies the properties of the state transition matrices, right? So the first one to satisfy is the origin one, right? The identity property. So that is if, say, we have t equal to t naught. So let's say if we have t equal to t naught, we expect phi of t naught to be equal to what? The identity matrix, right? So let's check it. Okay, so we get the cosine of in the first element here. In the first element here, we get the cosine of 0 is equal to what? 1, right? Sine of 0 is equal to 0. Sine of 0 is minus sine of 0 is equal to 0. Sine of 0 is equal to 0. And again, cosine of 0 is equal to 1. So property 1 checks out. I'm not going to go through all the properties. I just kind of wanted to show you that the properties hold. But you may see some checking of the properties in your homework. Great. So now, if we go through, if we apply the equation that we had before, again, that was x of t is equal to phi t naught x naught plus the integral of t to t naught phi t tau b of tau u of tau d tau. All right. So then this is going to be equal to we get the cosine of omega t minus 0. We're going to say our initial condition starts at 0. Then minus sine omega t minus 0. Sine omega t minus 0. And cosine omega t minus 0. And this matrix multiplied by 1, 0, the initial conditions. And then we go plus, this is just plug and chug, right? Plus 0 to t times cosine omega t minus tau minus sine omega t minus tau sine omega t minus tau and cosine omega t minus tau. And now all this multiplied by 0, 1. So if we look back up at this equation, we have no quote-unquote input signal, or we can consider b as just 1, and our input signal is 0, 1. So we're always forcing the velocity of our system, or the acceleration of our system, while we're not explicitly inputting into the velocity. Okay. All right, so plugging and chugging through this, and then we get a d tau. Right? Cool. All right, so then this is equal to, if we multiply 1, 0 here, we'll, in the first top element, we'll get the cosine omega t, and then plus 0 times the sine of omega t. And then the bottom one here, we'll get sine omega t minus sine omega t times 0 times cosine of omega t. So then plus the integral 0 to t. Okay, again, multiply 0, 1 times this integral. We'll get 0 times the cosine of omega t minus tau, and plus the sine, plus 1 times the sine of omega t minus tau. So this will be omega t minus tau. And then we'll get 0 times negative sine omega t minus tau, plus 1 times cosine of omega t minus tau. And that integrated with respect to d tau. All right, so now, make sure I'm lighting this up, equals, so this will be equal to, again, we'll get the cosine omega t minus sine omega t plus, take the integral of this guy, that'll give us 1 over omega, 1 minus the cosine omega t. This is sine omega t. And then at the end of the day, we'll get that the solution to our system is 1 over omega, 1 plus omega minus 1 cosine omega t. And then we'll get minus 1 omega minus 1 sine omega t. Which solves the initial value problem. Awesome. So today we went over solutions to linear systems, derivation of it. So we assumed the solution, showed that that solution is in fact a solution to our original linear time invariant system. And then we showed an example where we applied this to a linear oscillator system with a forcing function. And then we stepped through and found the solution to our system as being for both x1 and x2. Note that this is x1 and x2 of t here. Great. All right, that's all I have for you today.